Evening, everyone. We are going to start the class today. So, let us look into what we have seen in the previous class and then continue from that. So, in the last class, we looked into reaction with two adsorbed intermediates. So, where adsorption results in the formation of one intermediate, MHR plus, and in the next step, it forms MHR2 plus, and it is finally going into the solution. So because there are two adsorbed intermediate, we'll name them as theta 1 and theta 2. So in such a case, how we'll go forward is writing the mass balance for both adsorbed intermediates, theta 1 and theta 2. So first step is to write the mass balance, find out the steady state mass balance, find out the steady state surface occupancy of the intermediate species. Then we write down the formula for the net current, and from that we'll separate out IFDC, which is the current due to DC current, and then finally we'll find out IFAC, which will be written in terms of EAC. Then we have to find out what theta 1 dash, theta 2 dash, theta 3 dash, all those are, and rearrange it and find out YF. So I like when you have so then we looked into where can we use this, like we get the impedance plot and then we are proposing a mechanism and trying to fit them. We looked into assignment number 6, right? Okay. And in that we also saw like for confidence in predicting the model, how many DC potentials we need to have in order to map the your experimental data to the model. So we saw when the parameters are more, when you have the model parameters greater than the number of parameters from the experiment, you will have infinite combination. When you're taking it at different DC potentials, the electric parameters will keep on changing, but the DC parameter, the model parameters will not change. So there is so always your DC potential should be such that the kinetic parameters are lesser than or equal to the equivalent circuit model. We saw number of steps at electrochemical step is P, number of chemical step is Q, then you will have the total number of kinetic parameters as 2P plus Q plus gamma. Now when you have n adsorbed intermediate, you will have 2n plus 1 so this, and then when you divide this, you will get the number of DC parameters for which which is required in order to model the data. Then we saw the question related to that. Yes, that's where we stopped. Now let us go for this week's class, which is class 9. This catalytic mechanism, we'll first see the, okay, before going to that, let's see some questions from previous assignment that we didn't solve. I think it is from assignment number 4. Let me take that. Let me take the assignment number. Yes, it's assignment number 4. 13, 14, 15, and 16 questions are pending. We'll see this. So first question is, consider the following circuit used to represent the electrochemical systems. I'm writing down the question. Hmm. The capacity, the torque represent double layer capacitor. TV circuit determine the charge transfer resistance and polarization resistance. So the question is, a circuit is given, you have to find out the charge transfer resistance and the polarization resistance. Hmm. So this is the circuit which is given to you. So one question is, find out RT, charge transfer resistance, and the next one is find out polarization resistance. Okay, this is a question. So for such a circuit, when this circuit is given, you're aware that this part corresponds to the double layer behavior. So initial resistance plus double layer behavior. It is this part that corresponds to the Faraday impedance, which is marked in blue color. Okay. So RP, so like for ease, SNS, what I'm gonna do is I'm gonna simply name them like R1, R2, something like that. So it becomes easy to do. So this is RS. This is double layer capacitance. This is R1. This is R2, C2, R3, C3. Now RT is the value when omega tends to infinity. Faraday impedance when omega tends to infinity. Right? So what will happen? So resistor, it will not offer any resistance to what to say, I mean, resistance of a resistor is not dependent upon the frequency. So what does it affect? It affects the impedance of a double layer capacitance, which is 1 by j omega c of a capacitor. Now when omega tends to infinity, what happens to this value? When omega tends to infinity, this one tends to 0, right? This one will tend to omega of a capacitor becomes 0. That means it offers no resistance. So this can be simplified to something like, because it's not offering any resistance, it allows easy flow of current. I can reduce something to like this. It means, yeah, there is a double capacitor there along with R2 and R3, but they're offering negligible resistance. Now, what is the Faraday impedance? This is what is RT. Why? Because it's a case when omega tends to infinity. So you have three of them in parallel. So 1 by Z equal to 1 by R1 plus 1 by R2 plus 1 by R3, which is 1 by 1000 plus 1 by 250 minus 1 by 500. Because, or it is down, minus 500. So now if I'm doing this, it becomes 1 plus 4 minus 2000. So this is actually 3 by 1000. And then Z value becomes 1000 by 3 when omega tends to infinity. So what is the value you're getting? It is around 333.33 ohm, right? So when omega tends to infinity, what is it? It's actually RCT. So 333.33 ohm. Now let's move on to the next part, which is to find out the polarization resistance. So polarization resistance is RP. RP is when omega tends to 0. Faraday impedance when omega tends to 0. So let me again draw the figure. You have the solution resistance, you have CDL, you have a simple resistor, you have another resistor and capacitor. This is the figure you are having. When omega, so as told, then frequency changes, it has no effect on the resistance of a resistor. It will affect the resistance of a capacitor, impedance of a capacitor, which is 1 by j omega c. When omega tends to 0, this value tends to infinity. So it is offering infinite resistance. So current cannot pass through this way. When current reaches here, it's actually getting blocked. This will block, this will block. So ideally, no current is passing through this. So this means that all the current we are applying, it goes through the path which offers the least resistance or negligible resistance. In this case, and the only path that can offer the resistance is R1. Why? Because the path through R2C2 and R3C3 is getting blocked because capacitor is offering very high resistance. So in this case, the value of what to say, the Faraday impedance when omega tends to infinity, it becomes R1. So this means Rp value equal to R1. And what is R1 value? This 1000 ohms. So this is how you have to solve this question. Okay. Now let's move on to the next question. Now let us look into the next question. Okay. Which is so same way. The next question is also you have to consider the given electrochemical system. You have to find Rp and Rp. So I'll draw the circuit. So you have to find out what is Rp and Rp here. Okay. So as told like in the previous question, first you have to identify Faraday impedance ZF because it's from that we are going to find out Rp and Rp. So this one is Rs. This is double layer capacitance. So this becomes the ZF. Now, so it is nothing but yeah. So for ECNS, I'm gonna draw something like RX, CDL, this R1, this is R2, this is C2. Now how to move this for this question. So first let's go for RT, which is ZF when omega tends to infinity. When omega tends to infinity, we know 1 by j omega c, it tends to what? 0. So that means this part will offer negligible resistance. When that happens, what happens? The current can go like this, and it has two options. Can either go through R2 or C2. Because C2 capacitor is offering negligible resistance, all the current will pass through this. So this becomes R1 plus C2. And this C2, we know that is tending to 0. So all you'll have is a single resistance. And then the value is 25 ohm. Is that concept clear? Like when there are multiple paths for the current to flow, it will go through the path which offers the least resistance. So in this case, it is this path, R1. And then it will go through the capacitor. Because omega tends to infinity, capacitor offers zero resistance. So nothing will pass through R2. So your charge resistance will be reduced to R1 because C2 is already resistance of this impedance of C2 reduces to 0. Okay. Now let's look at the next thing, that is RP. So now I'll draw the same figure again, so it becomes easy to. So you have RS, you have CDL, this is R1, this is R2, this is CDL. So now when omega tends to 0, the ZF value, which is RP. When omega tends to 0, 1 by j omega c will become equal to infinity. So this is gonna offer infinite resistance. This means it will block the passage of current. So a current that comes this way, it can now not pass through the capacitor but through this way. And then it will go. So this reducing to something like this. Okay. Now what are the values? This 25 and 35. So your RP value equal to 25 plus 35 ohm equal to 60 ohm is the answer for this question. Okay, this is clear. I hope this is clear. Now, so this was kind of some exercise questions from 4 weeks portion. We didn't look into this, so I thought I'll discuss that now. Now we'll go on to this week's like practice of what we're going to do this week. Okay. So nextly, we are going to look into catalytic mechanism. Okay. So catalytic mechanism is where you have particular metal surface or some intermediate, so not metal surface, on some of the metal, you have an adsorbed intermediate which is actually catalyzing the reaction. So that metal goes into the solution as M solution. So it is catalyzed by a adsorbed intermediate, which gets replenished. Like first forms adsorbed intermediate, then it again reacts with the metal, where it forms the product, and we are regenerating it. The M adsorb. M adsorb remains as such. Okay. So we'll write the example question where it is one adsorbed intermediate. It's negative impedance. So let's write down the mechanism. It's a metal M. First step, it forms a adsorb and a release of an electron. Both forward and backward reaction can happen. Now, next step, M adsorb plus, on it again reacts with the metal surface, which is only forward reaction. It results in the formation of M solution plus, then M adsorb plus one electron. So you can see here M forms M adsorb. Okay, so this M adsorb, it helps in the formation of the metal reaction to form or go into the solution. Metal dissolution is helping. At the same time, this M adsorb which is here, which is consumed, it is regenerated over here. This means it's not consumed in the second step. Not consumed in the second step. Instead, it is helping in the metal dissolution, but without getting consumed. So that's how the mechanism is. So in the first step, you are seeing theta formation, or this means theta is formed. The 1B or the backward step, you see, consumes emits of plus or theta is consumed. Now in the second step, you see there is no formation or production of theta. So now let us first step is to write the mass balance, which is gamma d theta by dt. First step, you see the formation of theta, you have K1, 1 minus theta, which is a fraction of size occupied by mh plus. And in the backward step, you will see that MHO plus is getting consumed. Now, the second step, you don't see it is not getting consumed nor formed. So, we don't consider that step. It's a catalytic step. So, it is actually catalyzing the reaction without being consumed in the reaction. So, this is the step. Now, the first step is to write steady state mass balance. So, at steady state, gamma d theta by dt becomes equal to 0. So, you have K1 1 minus theta SF minus K minus 1 dc theta SS equal to 0. K1 dc minus K1 dc theta SS minus K minus 1 dc theta SS equal to 0. K1 dc equal to K1 dc plus K minus 1 dc theta SS. Theta SS equal to K1 dc by K1 dc plus K minus 1 dc. So this is the steady state mass balance equation and the steady state theta coverage for the adsorbed intermediate MHO plus. Now we have to write out what is the current density. So now how do we write for the current density? Give me a moment. Yeah. So here IF equal to, so what is the equation? It will consider all the steps, okay, where electron transfer is happening. So it becomes F. It's all single electron transfers. So N value is 1 into K1 into 1 minus theta minus K minus 1 theta plus K2 theta to 1 minus theta. So first step is to write IFDC, which is F into K1 DC 1 minus theta SS minus K minus 1 DC theta SS plus K2 DC theta SS into 1 minus theta SS. Now let us write IF. Finding out IFAC from it. IF minus IFDC will give you IFAC. For that, I'm gonna expand the bracket. K1 DC 1 minus theta 1. So just give me a moment. So yeah, I hope my slides are visible to you again. So we are going to continue. So now what we are going to do is we are going to find out IF total. Okay, so it is K1 DC 1 plus B1 EAC from this equation. Okay, 1 minus theta SS minus theta dash EAC minus K minus 1 DC theta SS plus theta dash EAC. Sorry, I made a mistake here. K minus 1 DC 1 plus B minus 1 EAC theta SS plus theta dash EAC plus K2 DC into 1 plus B2 EAC 1 minus theta SS minus theta dash EAC theta SS plus theta dash EAC. This is what you're going to get. Now I have to open up the bracket, but because I cannot, okay, I'll just start writing then IF equal to F into, you have K1 DC into 1 minus theta SS. Next is K1 DC B1 is K1 DC into theta dash EAC. Now from the next term you get K1 DC B1 EAC into 1 minus theta SS. So I write K1 DC B1 EAC into minus theta dash EAC, you'll get theta dash square. Theta dash itself is small value, so theta dash square is going to be very small. So we're gonna avoid that. Now the next term is minus K1 DC theta SS minus K minus 1 DC theta dash EAC. Now you have the next term K minus 1 DC B minus 1 EAC. Theta SS. The next term is K minus 1 DC B minus 1 EAC theta dash EAC. So there are two theta dash square. It is small, we can neglect it. Okay, so only that term will come. Now from the next term, K2 DC 1 minus theta SS into theta SS. Plus K2 DC 1 minus theta SS theta dash 2 DC into 1 into 1 minus theta SS to theta dash ESC. Now next term K2 DC B2 ESC 1 minus theta SS K2 DC B2 ESC I don't know this. K2 DC, B2 EAC. I don't know. B2 EAC into 1 minus theta SS into theta SS. Next same K2 DC, B2 EAC into minus theta dash EAC. Because you will get EAC square, that is also not possible. So I can get rid of that term. Okay. Next term again K2 DC, B2 EAC. 1 minus theta SS, theta dash EAC. So you'll get EAC square, which is also not possible. So this is the equation you're finding. So you got this much. Now the next thing is you have to get rid of few terms. Which all terms you can get rid of? All the terms with constants. So the constant terms become K1 DC, 1 minus theta SS is a constant. K minus 1 DC, theta SS is a constant. Uh, K2 DC, 1 minus theta. This is also constant. Now, what you can do is, you can get rid of these terms. Now, rearrange it such that you will have all the terms with theta SS together and the terms with theta dash together. So, you will get something like IF equal to F into, I'm going to take out the terms which has theta, what to say, theta SS here. Let's see. This term has a theta SS. This term has a theta SS. And this term has a theta SS in it. So if I rearrange them, you'll get K1 DC, B1, 1 minus theta SS. EAC I'll write together outside, okay? Minus K minus 1 DC, B minus 1 theta SS and K2 DC, B2 EAC, 1 minus theta SS into theta SS. This goes together. Now let's write the theta dash terms together. Theta dash terms are like this term this term and this term. So it is like minus k1 dc theta dash. I'm going to take it out. So dc minus k minus 1 dc plus k2 dc 1 minus theta ss, the whole theta dash, and this entire thing will be multiplied by EAC, which is written outside. Right? This much is clear. Now the next step is to find out the theta dash. The next step is to find out so that you have to write the mass balance equation, which is gamma d theta by dt, which can be written as j omega gamma, j omega gamma j omega gamma theta dash EAC k1 1 minus theta minus k minus 1 theta. So we are going to expand that on it. K1 dc 1 plus I'm going to write it K1 dc 1 plus B1 EAC 1 minus theta SS minus theta dash EAC minus K minus 1 theta SS plus theta dash EAC. Now we have to similarly remove the bracket and expand K1 dc 1 minus theta SS minus K1 dc theta dash EAC plus K1 dc B1 EAC 1 minus theta SS. The next step K1 dc B1 EAC into theta dash EAC will go because EAC square is not possible. Next is K minus 1 dc theta SS minus K minus 1 dc theta dash EAC, and the last term is minus K minus 1 dc B1 EAC theta SS. The last term K minus 1 dc B minus 1 EAC theta dash EAC wouldn't come because EAC square is again very small, so we can neglect it. Now let's get rid of all those terms which are constants. This goes, mm, this one goes, right? So now, which all terms do we have? Let us write that down. K1 dc theta dash EAC plus K1 dc B1 EAC 1 minus theta SS minus K minus 1 dc theta dash EAC minus K minus 1 dc B1 EAC theta SS. EAC is cut because it's common in all of them. Now let us rewrite such that the terms with theta dash, we get it together and then we'll proceed it, okay? J omega gamma plus K1 DC. So this term I have taken. Then which term comes? K minus 1 DC is there. The last term also doesn't have anything. Equal to, you have K1 DC B1 1 minus C dashes 1 minus theta axis minus K minus 1 B minus 1 theta axis. So we know theta axis is common. Okay. Now, if you see, we have got something like this. Now we have to simplify it. What is the first step? The first step is M adsorbed plus electron. So the forward reaction K1 dc to 1 minus theta equal to K minus 1 theta at steady state. So let us give substitution for K minus 1 dc, 1 minus theta as K minus 1 dc theta as over here. So when I substitute, I'll get theta dash 0 omega gamma 1 dc plus K minus 1 dc equal to K minus 1 dc theta axis B1 minus B minus 1. Right? So theta dash theta dash equal to B1 B minus 1 K minus 1 dc theta. You can also write in terms of K1 dc into 1 minus theta. That's also okay. Well, it's K minus 1 dc, right? Next, so this is what you have got. Now we have to substitute this in Faraday reaction, which is YF. Here you have got IF by EIS. And it's something into EAC. So I'm taking EAC this side. YF by EAC is IF by EAC is equal to E by EAC or the Faraday admittance. And that becomes equal to F into D1 K1 DC 1 minus theta SS plus B minus 1 K minus 1 DC theta SS plus B2 K2 DC theta SS 1 minus theta SS. Now it is K minus 1 DC minus K minus 1 DC my K2 DC. So I think I have missed out one term. So this term, this term, this term. With theta dash, I should get one more term, which becomes K2 DC, K2 DC, theta is K2 DC, B2 EAC. Yeah, that is K2 DC 1 minus theta SS, theta dash EAC. K2 DC, theta dash EAC into theta SS. Here it is minus K2 DC theta SS. Right? Comes along here. I missed out one term. So if I rearrange that, I'll get something like K2 DC 2 K2 DC minus K minus 1 DC minus K1 DC into gamma theta dash, which is B1 is B minus 1 K minus 1 DC theta SS by K1 DC plus K minus 1 DC J omega gamma. So this is the expression for YM. Okay. Now let us try to understand few things. So when voltage increases, okay. Now let's try to understand the expression. So this M giving M adsorbed plus electron K1 K minus 1. And the next step is M adsorbed plus M solution plus M plus electron. So now when potential increases, which all reaction increases. When you see there is an increase in the potential, we can say that the forward reactions will increase. K1 will increase, K2 will also increase. Whereas the backward reaction, K minus 1 will decrease. Now, when voltage, right, is that okay? Now, when voltage is just above OCP, what will happen? There is a small increase in voltage which will result in increase in current because it's kind of catalyzing the reaction and current will keep on increasing. But at very high anodic potential, when surface coverage at very high anodic potential, what happens? The surface coverage of M surface is so high. So will there be any free surface available for second step to happen? K1 reaction will increase, M absorbed will increase. Now this M absorbed has to react with vacant metal surface to form to allow dissolution and it is regenerating M surplus. But if there are all the vacant sites are occupied by M absorb, then which is the free available site for it to catalyze second reaction or for the second reaction to happen? No. Second reaction will slow down. All the first reaction will happen, second reaction will slow down and you'll see a decrease in current with the potential. So same thing. Surface coverage. So in this case, there is no vacant site and dissolution by catalytic mechanism decreases. So this means hence current potential. So in this case, you will have a graph something like current potential. Potential increases, current increases, and after that point, it reduces. Okay. Now, this is what is a behavior, and that's why we are saying it is having catalytic mechanism on that subintermediate, it's having a negative impedance. So this at lower over potential. So I said it has two behaviors. Lower over potential, you have current increases with potential. At high over potential, you'll see current decrease with potential. So in the higher over potential, you'll be seeing a negative impedance. Uh, that's what this mechanism is talking about. So is this clear? Now let's look into assignment questions regarding this, and then we'll look into the Fromkin isothermal. Let me take the assignment. So now let's look into the assignment question. I'm taking them. This is assignment 7. There are some numerical problems based on this. We'll look into that. So question number 1. Consider the reaction. MHO plus electron. MHO plus metal. So you can see MHO, it's coming out as MHO. So this also means it's a catalytic reaction. So kinetic parameters. are given by K10 equal to 10 to the power 9 minus 9 mole per centimeter square per second. V1 equal to 10 volt inverse. K minus 1 0 equal to 10 to the power minus 8 mole per centimeter square per second. V minus 1 equal to minus 10 volt inverse. K2 0 equal to 10 to the power minus 8 mole per centimeter square per second. B2 equal to 10 volt inverse. Gamma equal to 10 to the power minus 8 mole per centimeter square. Now the question is that VDC equal to 0.1 volt versus OCP. The fractional surface of M adsorbed is given by what? We have to find out what is fractional surface coverage. So first we've already done it, but still let's do it. So fractional surface coverage d theta by dt. So the forward reaction is K1 into 1 minus theta. Backward reaction is minus K minus 1 theta. Do we consider the second step? No, because it's a catalytic reaction and what is consumed is formed in the next as product. So you don't need to consider that. Now it's steady state. K1 dc 1 minus theta ss minus K minus 1 dc theta ss equal to 0. So K1 dc by dc plus K minus 1 dc equal to theta ss. This is what we have to find out. Now what is K1 dc? It is K1 naught exponential of B1 EDC. K minus 1 dc equal to K minus 1 0. K minus 1 0 exponential of B minus 1 EDC. So now let's substitute and find it out. Okay. K1 dc equal to 10 to the power minus 9 exponential of 10 into EDC is 0.1. So it is 10 to the power minus 9 exponential of 1. Which is, let's do the calculation. That is 2.718 to 10 to the power minus 9. Okay. Now, just give me a moment. Yeah. Now K minus 1 dc equal to K minus 1 0 exponential of d minus 1 e dc. So K minus 1 0 equal to 10 to the power minus 8 exponential of minus 10 into 0.1. Just 0.367. This is 10 power minus 8 into 0.368. And like this in terms of 10 to the power minus 9. So let's make this also like that. Becomes 3.68 into 10 to the power minus 9. Now, what is theta S is? Theta S is equal to K1 dc by K1 dc plus K minus 1 dc. So it is 2.718 into 10 to the power minus 9 by 2.718 into 10 to the power minus 9 plus 3.68 into 10 to the power minus 9. So you get 2.718 by 2.718 plus 3.68. Let's do the calculation and find out the value. So I'm getting 0.428. So in the question, given that the answer should be between zero point 0.4 and 0.44. So yes, my answer is between those two values. So this is okay. Now the next question, which is also a variety of okay, now let's write the next question as consider the same reaction. Okay, I'm just writing down the reaction. If the reaction is in kinetic limited region, if it's in kinetic limited region, the maximum number impedance NPTL class. If the reaction is in kinetic limited regime, the maximum number of loops expected in complex plane plot. So the question is, there's the catalytic reaction which is happening, which we have seen now. So it is happening in kinetic limited regime. Then what are the maximum number of loops you can uh, now the maximum number of loops that are expected in complex plane plot is how much? So for a complex plane plot, you know that the number of loops will correspond to 1 from the adsorbed intermediate. Okay, from the number of adsorbed intermediate, and one extra loop from the double layer capacitance. So for irrespective of any reaction, one of them will be coming from this. Additionally, how many adsorbed intermediates are there? So here, to list one adsorbed intermediate, which is M adsorbed plus one from the double layer capacitance. So totally it is 2. Now the next question. So I hope this is clear. Now let's look at the next question. Consider the reaction again, the same reaction. Next step, MHR plus the metal. It forms MHR plus M solution plus electron. The kinetic parameters are given by K10, V1 10 volt inverse, K minus 10 10 to the power minus 8 mole per centimeter square second. V minus 1 equal to negative 10 volt inverse. K20 equal to 10 to the power minus 8 mole per centimeter square per second. V2 equal to 10 volt inverse. Gamma equal to 10 to the power minus 8 mole per centimeter square. Right, TTC equal to 0.1 volt versus OCP fractional surface. Sorry. This we already done. So it has a subpart which is Faraday current is this dash milliamp per centimeter square. So basically, you have to find out the Faraday current from in this question. So we already found out what is K1 DC and K2 DC. Sorry, K1 DC and K minus 1 DC. What are it? K1 DC is 2.718 10 to the power minus 9. K minus 1 DC is 3.68 into 10 to the power minus 9. Now we have to find out what is K2 DC, which is K20 exponential V2 ADC. So K20 is 10 to the power minus 8 exponential 10 into zero point 0.1. So which is again 2.718. Sorry. It's wrong. I've made a mistake here in the value. It is exponential of 1, 2.718 into 10 to the power minus 8. This is the value you will get. Now what is IF value? IF value is equal to Faraday constant into R1 minus R minus 1 plus R2. R1. Okay, so now let's find out R1, R minus 1, R2, etc. Okay, what is R1? So we already know theta value from this question, which is 0.428. Now R1 is equal to K1 DC into 1 minus theta SS, right? 2.718 into 10 to the power minus into 0.428. So which value is 2.718? 0.163 into 10 to the power minus 9 mole per centimeter square. Now R minus 1 is equal to K minus 1 DC theta S because it's a backward reaction. M adsorb giving M adsorb plus electron giving M surplus. R2 equal to K2 DC 1 minus theta into theta. Point 428 into 0.428. So 2.718 into 0.428 into 1 minus 0.428. You will get 0.665 into 10 to the power minus 8. So because all of the others are in 10 to the power minus 9, I can write this as 6.65 into 10 to the power minus Okay, there's the value. Now, IF is equal to F into R1 plus R minus plus R2. R1 is equal to 1.163 into the power minus R2 6.65 into the power minus 9. R minus 1 1.575. So I'm going to substitute everything. I'm going to take 10 to the power minus 9 outside. The value is so I'm getting 0.00601, sorry, one more zero, ampere per centimeter square. Okay, in milliamp per centimeter square, I have to multiply this by 10 to the power minus 3 to get them in milliamp per centimeter square. This is the value I am getting. Now let's see what is the range at which they are expecting the values. Yeah, 0.6 to 0.7. So my answer comes in that range. So this is how you have to solve this question. Now to do the next question, we have to look into Fromkin isotherm, which will do it in the next class. Before that, there are some other questions we have to solve. We'll do it now. A mechanism is described with 15 kinetic parameters. It contains readsorbed intermediates. The maximum number of loops that can appear in a complex plane plot is, so I said the number of loops are always equal to number of absorbed intermediates. Maximum number of loops. Let me be clear. Maximum. It can be lesser than this also. Number of adsorbed intermediate plus one loop from double their capacitance. Right? So here they have already mentioned number of adsorbed intermediate is 3. So it becomes 3 plus 1 equal to 4. Okay. So 4 is the answer. Now, this has a second part. In the above question, the total number of electric elements required to model the reaction, that is only Faraday part, without considering double layer capacitor, is how much? So, so they're asking how many elements are required to model the Faraday impedance. So for every adsorbed intermediate, for each adsorbed intermediate, okay, it is modeled by using a pair of R and C. So it will have an R and a capacitor, or R and an inductor. That's how we have modeled. If you remember any of the circuit, we did draw something. Yeah, here. We said there's a Faraday impedance. You see, R and C will come in a pair. Now take this also. R and C are coming in pair. R2, C2, R3, C3. Okay. So each pair of RC corresponds to one absorbed intermediate. And apart from that, it will have an additional resistance, like the one over here or the one over here. This one becomes the charge transfer resistance also. So it's a combination of this individual R with the pair of RC corresponding to every absorbed intermediate that forms a Faraday impedance. So in the question, coming back to the question, a mechanism with 15 parameters and it has 3 absorbed intermediate. So 3 absorbed intermediate. This means so 3 absorbed intermediate means 3 pair of RC. So this means 6 electric elements. Now I told there is N plus 1 resistor. So this means the total will be how much? It will be 7. 6 plus 1, 7. So there is the answer for the next question. Now this next question is to model a system with above mechanism, the minimum number of DC potential at which EIS data is taken is in the last class. So the question is If we have to model the same system, how many DC potentials are required at which the impedance needs to be taken so that the model it can be modeled. So in the last class we saw that the number of DC potentials should be always lower than or equal to the number of parameters. In the sense, the not the DC parameters, such that DC potential should be such that the kinetic parameters we get will be lower than that of the electric parameters. So in this one mechanism, okay, let's see this page. The steps are M, M adsorbed plus electron. So in this case, what are the number of electrochemical steps? How many electrochemical steps are there? You have one forward, one backward, and the second step. So totally three steps. Number of chemical steps, zero. And for each electrochemical step, there will be Ki and Bi. So it will always come in pairs. So number of kinetic parameters resulting from electrochemical step is 3 into 2. The chemical step, 0. And the number of, you also have gamma. So gamma is also kinetic parameters. You have 7 kinetic parameters. Now, how many intermediates do you have? So kinetic parameter 7. Now, number of adsorbed intermediate equal to what? Only one adsorbed intermediate. So number of RC parameter will be how much? One RC, one resistor, one capacitor for one adsorbed intermediate. So number of RCs required is one RC is needed. So this means two parameters, that is one resistor and one capacitor, right? Apart from that, I told you the number of parameters will be on additional resistor in addition to the pair of RC. So number of EEC is going to be 2 plus 1 equal to 3. Now, I already told you that the number of DC potentials should be such that kinetic parameters should be less than or equal to number of equivalent electric circuit, because only then you will have more number of electric parameters, or else you will have infinite number of parameters, and it can take more number of parameters means it can take infinite solution. So how do you find that out? It is 2p plus q plus 1 by 2n plus 1. 2p plus q plus 1 here is 7 by number of equivalent electric circuit is 3. So just 2.333. So we have to always round that up, not round it down. So the value is 3. 3 DC potential. So is that the answer given there? Yeah. So yeah, that's all for today. Now we'll look into the rest of the chapter in the coming classes. Okay. If anyone has any doubt, you can post it. Else I can clear it in your next class after you go through the video. Okay. Thank you.